So, good afternoon, everybody. Today and October 4th, using these two times, I will speak about space robotics. And today's topic is about the a mobile robot for lunar planetary exploration missions. My name is Kazuya Yoshida. I'm speaking from Tohoku University, Japan. And so now I will switch the screen uh, to my presentation file. Now I would like to go on the next topic, that is sensing and navigation. And so for the exploration of the completely unknown environment, situation awareness is very, very important. And actually, this is a picture of the NASA's Mars rover, and which has a pair of stereo camera and mounted on such a large scale, a pan tilt mechanism. By using two motors, pan and tilt, and rotate this stereo camera, then we can get the image of the environment, and also because of the stereoscopic analysis, we can get the distance to the some features, the rocks and mountains and over the surface. So this is a very established and promising technology. But from the research purpose, we have been interested in a different device to directly measure the distance, which is a laser ranging sensor. So in this black shape a tool, there is a laser diode and a spinning or scanning mirror system, and then a project infrared laser spot. And then because of the scanning rotation, and that this laser spot can rotate, then at every millisecond that we measure the distance of the projected point, because of if that object makes a reflection, so we can measure the distance based on the time of flight of light emitted by a laser diode. And so then in such a way, we get this type of the spot of the reflection. So this cloud-like the reflection points are called a point cloud, a point cloud of the reflection points, and a point cloud of the reflection from the object. And so, which is not really visible or useful, but just if we put these three-dimensional points onto the XYZ coordinate frame, then the situation becomes much more visible and understandable. Then from this picture, we see that there are some flat areas, but in front of this vehicle, we have some obstacle. And another obstacles are there and there and there. And then right behind the obstacle, that because of the laser beam interrupted by this the obstacle, so there is no reflection over there. So this area is called occluded. So the occluded area because of occlusion. So anyway, we can identify the environment in such a way and categorize which is safe and accessible, which are the obstacles and which are the occluded area. So then just for example, if we give a vehicle to go that way, but we can develop the algorithm, very simple algorithm, because of this obstacle, he cannot go there directly. So then he need to find some intermediate point. So closest point to the goal, then find out the accessible path to the midpoint goal. So then anyway, go there first, then make another measurement, then find out another route to go to the given destination. For example, in such a way that we can write the path planning and execution type of the algorithm based on the result of such a laser-based sensing capability. So anyway, for the demonstration of this system, we developed the testbed called El Dorado 2. The El Dorado, it's a Spanish word, means gold or golden because it has a golden body. And this weighs about 20 kilograms, which has 4 wheels and a steering axis also. And on the top of this vehicle, we mount a laser scanner. And this makes scanning of the environment, and so that we get the location, position, and shape of the obstacles quite precisely. So then we conducted some demonstrations using many different opportunities, and this was one of the IEEE conference. The conference organizer prepared such a test environment for us. Anyway, this shows the kind of the lander, the landing vehicle, and go down on the egress and touches on the surface of the remote planet. Then remote planet has some scattered obstacles, and that based on the laser ranging sensor-based sensing system, it scans and then obtain the distance and also build a map of the environment and go to the destination. So this field was very small for us and just a 10 meter by 10 meter. So it was relatively easy to travel from there to there. And so in this case, we use a very simple algorithm: stop, measure, and go. Stop, measure, plan, and go, and repeating such a cycle. And so anyway, afterward, we get this kind of the map of the given environment. So that the range of the laser sensor, in that case, not so big. This is 10 meter, but maybe the ranging capability is 5 meter or something. So then after, but according to the travel, we accumulate the data, and then connect the many different patches. And finally we get the map of the whole environment. So this technique, and particularly we don't know anything a priori for the environment, but we know that the environment is static, so the location of these obstacles doesn't change. And then maybe we can use some additional information, but usually the laser or visual images are only the reliable information. So then how to construct a map and also get the location of the vehicle. So this technique is today a very famous research topic for the mobile robotics community. That is called SLAM, simultaneous localization and mapping. So people call it SLAM. And the SLAM technology is one of the fundamental technique for the mobile robotics. So if the surface is very rigid, and we can ensure that the wheel doesn't make any slippage. So then we can use odometry-based information. But as we know, the surface of the moon or Mars has a soft, deformable soil, and the slippage is always a problem. So that wheel rotation-based odometry doesn't work very well. So the laser sensing and stereo vision, image-based analysis, these kind of techniques based on this information is very considered reliable and useful. So we have conducted another demonstration for using the same the robotic testbed. But this is the demonstration for the human-based control, but with a long distance. So to simulate the situation between, for example, Earth and Moon, we used telecommunication satellite, which is located on the geostationary orbit. So the runtime and transmission is about a 0.5 to 1 second, or sometimes maybe more than 1 second. And in such a situation, we would like to see that if the people, my student, can drive a mobile robot in such an unstructured environment. So actually, this was a demonstration. It's a kind of the structured environment. This is just the inside of the building. And so then we know that the surface is almost flat, floor is flat, and we have vertical walls. But still, we don't know any a priori information of the environment. So the one simple idea is many people may ask, why don't you use conventional camera? Mounted, if we mount the web camera on the top, we can get the image of the environment. And however, we use the satellite-based communication network, and sometimes and usually we have a latency problem, and sometimes the bandwidth is very critical to transmit the high-resolution video stream. And in such a case, such a laser-based three-dimensional information is much more useful and powerful. So for this XYZ coordinate, we just need a very, very small packet size, a small data set. But this describe the this is a flat floor. We have such and such vertical walls. So we should go there. We should go straight forward in this situation for a few meters, but we should not go to the left or right in this particular situation. So the remote operator can recognize at least that which is a safe direction, which is unsafe or impossible directions in such a kind of a quick decision can be made based on the laser sensor-based measurement system. So then, and another advantage of such a laser-based measurement system is, as I mentioned, after the accumulating data and connecting all the patches, and we can build a map of the whole environment in such a way. So then finally, after the exploration, we get the map of the this whole area. So this is the relatively easy case for the relatively flat floor environment. But today we have a technology for the much rough terrain in which the soft deformable soils with a lot of the wheel slippage. We still build a map, a relatively precise map of the completely unknown environment based on this type of technology. So now let me go on the final topic of our recent development of the test rover for possible future lunar exploration. So our new rover still has 4 wheels, but relatively small and lightweight. It's about 10 kilograms in total. And here we have a laser scanner again. But we also have another type of the camera. This provides the omnidirectional images. So I will explain it. But before that, I would like to show you the video clip about our recent field testing in one of the Japanese volcanic area. Yes, I'm sorry that the video is relatively slow, but and the volcano is a very unique and interesting environment. I don't know that in Bulgaria there are volcanoes, but in Japan and there are many volcanoes and hot springs and earthquakes. And anyway, the volcano environment look quite similar to the lunar or planetary environment. So, and this is another volcano which has more scattered rocks. And from this you can see the performance of the passive suspension system. So if the obstacle, the height is shorter than the wheel radius, this rover can go over relatively easily. So at this time that we didn't have, we had a relatively small power in the wheel motor, but still it can go on. So after this experiment, we increased the power of the built-in motor in the wheel axis. But anyway, this is a quick introduction of the vehicle and the mobility. But one of the point here is Omni camera. This Omni camera has a very yes, this is the close-up, the omnidirectional camera. And this is just a mirror which has a hyperbolic surface, and the real camera stays the bottom and look up this mirror. Then we get such an image. So this is a 360 degrees of the image, and because of the reflection of the hyperbolic mirror, and we get such a circular image of the environment. And this camera is very, very useful and powerful. So that this is from our expedition in the volcano area. So the original image is in the bottom, and 360 degrees of the omnidirectional image is obtained. And then after, as a post-process, we make a simple coordinate transformation. We can get such an XY coordinate frame in the panorama image of the environment. And this image shows the location of the nearby obstacles and mid-range mountains and very far mountains. So from close vicinity to the far distance, we get the features of the mountains and obstacles and rocks and so on. And another advantage is that we can see that vehicle body itself. So one of the big concern in a real remote operation, and many people concerns about if the vehicle itself is in a good shape. So usually a conventional camera mounted on the vehicle cannot give us much information about the figure of the rover itself, but automatically by using this mirror type omnidirectional camera, we get the vehicle itself, the image of the vehicle itself very easily. So and then we discussed the laser sensor, and here we have another type of laser sensor in this new rover, and which uses a MEMS technology, MEMS-based scanning mirror. And so the scanning angle is not that large, but we get such the distance data for the point of projection and projection and reflection. And then we superimpose of the measure data onto the circular coordinate for the omnidirectional camera. So then, okay, this is one of the examples that the height of this area is low, but the height of this point is large because of the rock obstacle. And so this is the close-up. And yeah, so just to snap this images tells the that we have obstacles, and so then because of this data, we can tell the height and distance of this obstacle. Then remote operator can very easily recognize the situation, and then we need to make an avoidance maneuver or something like this. So that we developed this type of rovers because we are very much interested in the lunar project. And so at the very beginning, maybe 10 years or 15 years ago, I thought that we should, as a nature, as a principle of the function of the national university, that we should contribute to the Japanese national mission. However, the space missions in any nations goes very, very slowly because of the budget and political reasons and any reasons. The project can delays or maybe canceled, and many things could happen. And so, meanwhile, we found such a very, very unique private-based challenge for the lunar exploration. that is Google Lunar X Prize. And X Prize is a private, non-profitable foundation that gives the challengers a cash prize. And for this lunar challenge, the 30 million US dollars are prepared. And if you first land on the moon and travel over the 500 meters and send back to the high definition video images, um, organized and prepared, conducted by private entity, you will get 20 million US dollars for the first and $5 million for the second team, and another $5 million for bonus prize. So this is a very good idea to encourage the private entities to try to go to the moon and develop the technologies. And so the challenge is very important. So at the peak time, the 29 or more than that teams subscribed for this competition from all over the world. And today, the number of the teams has decreased because of the some difficulties in technology and finance. But I personally participate in the Japanese team. And from Japan, there is only one team challenging to this competition. But so there's such a large number of teams that all the teams has a different ideas and scenario and strategy for the design of the rovers and means to arrive on the surface of the moon. But those activities itself accelerate and encourage many people for the future lunar or space missions. So our Japanese team has a name Hakuto. Hakuto is a Japanese word meaning white rabbit. Rabbit, I'm sorry, rabbit, and animal. And that jumps on the surface. So the Japanese mythology tells that on the surface of the moon, there lives a number of the rabbits. And so white rabbit is a kind of representing image of the moon. So that's why our rover has a white color. So this is a white rabbit. And so, but this is a four-wheel design. But if because of the payload capacity of the landing vehicle, we may need to change our design for a much more compact body. So in such a case that we also prepare the two-wheel configuration, which requires much smaller volume and mass, but still that this vehicle can have enough mobility for the surface of the moon. But anyway, so we are currently working on this type of the rover development. And so as a okay, this I'm sorry that this slide has so many letters. But today I spoke about the robotics for lunar and planetary exploration. And my topic are divided into the vehicle, mechanics, and sensing and navigation tools, and with a particular focus on wheel slippage. So vehicle design, the local bogie suspension is a very well-known and promising design, but still this has a limitation, particularly in case of the soft soil environment. And for the sensing and navigation, the stereo camera technology is already established and very strong potential, has a very strong potential, but the laser lensing sensor also has a very strong potential, as I showed you tonight. And particularly speaking about the locomotion on the surface of the moon, which is mainly covered with very soft, fine dust-like material, we need to pay a lot of attention to the wheel slippage. So the wheel traction control. Traction control is not really an appropriate word, but anyway, the wheel control it becomes very, very important to avoid the situation getting stuck in the sand dune. So that's all of my presentation tonight, and then I hope you enjoyed my talk, and I'm happy to answer to your questions.